In this video, we're going to discuss intensity. Intensity is equal to power per unit area. So remember, power is energy per unit time, which means we're really talking about the amount of sound energy at a particular moment that is passing through a specific surface area. And remember, this energy comes from the fact that the sound wave is compressing whatever medium that it is traveling through. So that compression is a force over a distance, which is work done, and that work means that there's a change in energy. So we're talking about how much energy per unit time traveling through a specific surface area. That is what intensity is. Since intensity is power over area, our units are going to be watts per meter squared. And because area is going to have a distance component, which we'll discuss in a moment, intensity decreases with increasing distance from the source. So in this particular course, we're going to assume perfect spherical waves. So think about if you throw a pebble into a pond and you see those nice circular waves coming out. Here we're going to assume a spherical wave, meaning that the waves come out in all dimensions, so all three dimensions equally. So I'm stuck with drawing what look like circular waves because of the nature of a whiteboard. But remember, this is a cross-section of a sphere, so you can imagine different size beach balls all on top of each other. And we sort of call these the wave fronts, or that's where you would find the crest of the wave versus the open area, which would be the portion which we would call the rarefication or the trough of the wave. So the crest is where you get the compression, trough is where you get that region of rarefication. So because we're assuming spherical waves, our area in our denominator is going to be 4 pi r squared. Now if we assume that there is no energy lost as the sound wave travels away from the source, we can derive a specific relationship between intensity and distance from the source. So we're saying that P1 equals P2, so as the wave travels away from the source, the rate at which energy is being changed per unit time is remaining constant. So we're not having any source of diminishment in the amount of energy or the rate at which it's being transferred. That means that I can sub in the idea that intensity is equal to power divided by area, or arrange that to say intensity times area is equal to power and sub that in on both sides. And then I can sub in my relationship for area for a spherical wave. I can cancel out the 4 pi's on either side and we get this relationship that intensity 1 times r1 squared is equal to intensity 2 times r2 squared. So that we can have a source and we have our spherical waves coming out of that source. And we can say that we have an intensity here and an r value here. And then as we get further away from the source, we're going to have a different intensity and a different distance, obviously. But that must follow this relationship here. So if you have intensity 1 and distance 1, you can find intensity 2 at a different distance from the source.